Hello, everyone. Welcome to this presentation for AIM 2023. I'm Chao Qing from University of Toronto Institute for Aerospace Studies, and I'm about to introduce our paper, Perception-Aware Image-Based Visual Servoing of Aggressive Quadrotor UAVs. This talk will start with a brief introduction, the objective and key ideas of our works. We'll present the feature representation, the full system dynamic model, the constraint to ensure target visibility, and the optimal control problem. We will also highlight the key distinction between our approach and the virtual camera approach. Finally, we will showcase the experimental and simulation result of our method in several challenging visual serving scenarios, demonstrating how perception awareness enhances the robustness of image-based visual serving under aggressive maneuver. In the following context, we will refer image-based visual serving as IBVS. We know that aggressive UAV maneuvers pose challenge to IBVS. This is primarily due to the limited field of view of onboard camera, making it susceptible of losing track of target during large rotations. This problem is even worse in underactuated robots such as quadrotors, where rotation is coupled with translational motion. However, aggressive maneuvers are still desirable for certain UAV tasks, such as landing. For example, aggressive maneuvers enable the drone to land on the target more quickly and thus save more battery power. Hence, our objective is to bridge the gap between IBVS and aggressive UAV maneuvers. Specifically, we propose a control framework that can automatically balance the level of agility with the requirement of target visibility. In other words, the controller solves how aggressive it can be under the visibility constraints. To access the true target visibility, we need to know where the true visual feature is. However, many existing work have replaced the true target with a virtual target, which is expressed in a virtual camera frame. Our first idea is to design a new scheme that allows us to model the true target instead of a virtual one. Our second idea is to predict the future visual feature location using the quadrature dynamics and image kinematic models, and then apply visibility constraints over a future time window. This ensures that any controls that potentially fail the visibility constraint will not be produced. We incorporate this idea into a nonlinear model predictive control, which we refer as NMPC frameworks, and solve the control problem online. The contributions of this paper are listed below. To enable modeling the true target visibility, we propose a novel rotation compensation scheme to remove the need for a virtual camera frame. A generic framework to balance flight agility and perception awareness is proposed, which can be easily modified to different UAVs under different flight applications. Furthermore, we demonstrate the real-world performance of our method under aggressive flights, such as tracking a fast-moving object. For scenarios which are difficult to test in the real world, we provide sufficient simulation results to confirm the reliability and efficacy of our method. Let's start with the first part, system modeling. Before delving into the methodology, we first want to clarify the rationale behind our selection of feature representation. A visual feature refers to a pixel in the image that corresponds to the target object. Since the distance to the visual target is generally unknown, it provides only 2D information. In the case of underactuated system, we prefer to project such a visual feature onto a unit sphere to leverage the passivity-like property. Apparently, there are multiple ways to parameterize a point on unit sphere. The most direct and straightforward approach is to utilize a 3D unit vector. As depicted in this slide, the green arrow starting from the camera origin and terminating at the surface of the sphere can be used to represent a visual feature. However, In this work, we use a totally different feature representation. It is based on the rotation between the 3D unit vector and the optical axis of the camera. As illustrated by the red line in the figure, this rotation can be obtained by calculating the angle axis vector between these two vectors. Employing a rotation as an underlying implementation offers multiple advantages. The most important one is that it offers a smooth image kinematic function over the whole two-sphere manifold. This idea originates from visual localization, and we introduce it into visual servoing for the first time. We provide a detailed derivation of the full kinematic function in our paper. Now we introduce the full system dynamic model. It can be seen that the camera is rigidly connected to the flying platform, and therefore, any thrust change will eventually propagate to a change in pixel coordinate of the visual feature. To precisely capture this relationship, we need to take into account both the quadrature dynamics and image dynamics. And thus, the system states to be composed of the velocity of the drone, VW, the orientation, QWB, the visual feature implemented as a rotation, Q, and the distance to the target object, R. We assume that this state can be measured by our onboard state estimators. The control command consists of the collective thrust and body weight of the drone. There are three constraints considered in our works. The visibility constraint enforces the visual feature to stay within the specified image bound. The function pi maps the rotation to pixel coordinate of the visual features. We also define a time to collision constraint to avoid sharp breaks when UAV is close to the terminal position. We observe that when a sharp break occurs, the drone needs to produce a large rotation for the drone to decelerate itself, which is detrimental to target visibility. The last constraint is related to the actuator constraint, which is thrust and body rate limits in our context. Like a standard NMPC quadrotor controller, we have four objective functions. The first one corresponds to position check, in which a positional vector is calculated by using the state at time t. We can indeed think of this process as a form of rotation compensation, but without explicitly defining a virtual camera. The remaining terms include velocity tracking, UAV stabilization, and control regularization. Finally, we formulate an optimal control problem by using the system constraint, dynamics, and objective function defined above. And we send it to an NMPC solver, Arcado, which solves this constraint nonlinear programming online. Lastly, we would like to emphasize the key difference between our approach and the virtual camera method. Put simply, our method first predicts the motion of the visual feature and then conduct rotation compensation. The virtual camera approach follows a reverse order. It first compensates the rotation by transforming the visual feature into a virtual camera frame, and then predict the future motion using the image kinematic model defined on the virtual camera frame. There's a huge advantage in doing the compensation after feature prediction like what we did, because it allows us to define the visibility constraint in the original image frame, and the true target visibility information can be preserved. As a result, the visibility constraint defined in our method remain valid during aggressive maneuvers, whereas those virtual camera methods cannot. This phenomenon is illustrated in these slides. It can be seen that as the quadrotor pitch forward, the target will leave the camera field of view, denoted as the green cone region. Our method can quickly identify such constraint violation via state prediction and prevent such a motion. In contrast, since the target can always stay within the virtual camera frame, the virtual camera method has no response to such a problem, and eventually fail the visual servoing task. In the second part, we would like to share the result we have in simulation and experiments. This is the control diagram we use to implement the whole control system. The green part stands for the core control algorithm we introduced in previous slides. The computed thrust and body weight command are tracked by a low-level body weight controller. Note that there is an onboard camera on the drone, which outputs the RGB image at certain frames per second. The target object is detected by a learning-based object detector, YOLO V5, and the distance to the target is estimated by comparing the size of the resulting bounding box with the known object size. This is the platform we use in the experiment. We use a circular gate as a target object. This is the video of our experiment. The left figure shows that our method can keep a 100% target visible rate within all reference velocity settings. We know that the larger the reference velocity, the more aggressive the quadrotor may behave. The right figure compares the maximum speed and pitch angle the drone reaches under different reference velocity. We can see that our method begins to limit the quadrotor rotation and speed when the reference velocity gets higher. This result demonstrates that our method can appropriately restrict the quadrotor's agility to ensure target visibility. To sum up, we propose a robust IBVS method to enable aggressive visual serving tasks with underactuated UAVs. We open source our code to facilitate the comparison with the future method. In our future works, we will take the dynamic of the target object into account to further increase the prediction accuracy of visual target motion. We will also eliminate the need for yaw estimate by incorporating more visual features. Last but not least, we will try to extend the proposed method to a more high-speed scenario, such as autonomous drone racing.